Okay, next is the insertion sort. Okay, the process is that elements inserted into suitable location resulting in a sorted list. And so if elements in a column fulfill the condition of sorting, sorting is not done, and then move to the next column. Okay, so the condition here is either ascending or descending. If the condition for ascending would be the first element compare less than with the second element. If let's say the condition for descending, it means the first element will compare larger or bigger than the second element. So once the condition is true, then we can insert that element into the right locations. So until the result in a sorted list as desired, either ascending or descending. Okay, here is the example of insertion sort. I'm taking from the studytonight.com. You can see here in the source link, and then you can see that we have 6 elements in array. So array of 6 start with 5, 1, 6, 2, 4, 3, and then the index 0 until index 5. So when we want to do the sorting using insertion sort, we start with the second element, the index 1, okay, and then we compare with the first element. Is it 1 smaller than 5? Yes. So the condition is true. That means we need to move 1 to the beginning of the list, and then 5 we move backward. Okay, so that means we need to move 1 and 5. It seems like these two elements do the swapping, exchange values. Okay, so then it will become 1 and 5. Now we have start with index 1, the second element, then we move to the third element, 6. So 6 compare with the first element. 6, is it 6 less than 1? No. Is it 6 less than 5? No. So 6 remain as it is, not going anywhere. Now we move to the next loop and move to the fourth element. Okay, so the fourth element compared with the first element. So 2 is less than 1? No. 2 less than 5? Yes. That means 2 need to be inserted between 1 and 5. So you need to move 6 and 5 at the back, and we'll move 2 before the number 5. So and then we become 1, 2, 5, 6. Okay, so 2 will be inserted between 1 and 5. So 6 move to the fourth location, number 5 move to the third location, and then the number 2 will copy, go to the second element. Okay, then we continue the loop, continue the process. Now is at the fifth element. Okay, so 4 compare with 1. Is it 4 less than 1? No. 4 less than 2? No. 4 less than 5? Yes. That means 4 need to be inserted between 2 and 5. So before we can do that, we need to move 6 to the 5th location, 5 to the 4th location, and then number 4 will copy to the 3rd location. Okay, and then we continue again with the loop. The next will be the 6th element, number 3. So 3 will compare with the first element. So 3 less than 1? No. 3 less than 2? No. 3 less than 4? Yes. That means we need to insert 3 between 2 and 4, and then of course we need to move the 4, 5, 6 at the back, so that 3 can be copied to the 3rd element. Okay, now this is all about the insertion sort. Another example here, we using the partition, and of course you can look into how the loop using J index would be beneficial for the insertion sort. Okay, of course you start with the second element, compare with the first element. So 2 compare with 5, 2 less than 5. Yes, that means 2 need to be inserted before 5, 5 need to be copied and moved to the right. So it seems like 2 and 5 become an exchange value, so 2 and 5. Now after this partition, we move to the second partition, and with the third element, number 4. So 4 we compare with 2. 4 less than 2? No. 4 less than 5? Yes. That means 4 need to be inserted between 2 and 5. Same goes to the rest of the process until the list is sorted in ascending order. Okay. So what will be the efficiency for insertion sort? So the worst case scenario for this algorithm is when a list in the reverse order from desired order. So that will be a difficult for you to do the insertion sort, the worst case. And then the formula that we have construct to do the insertion sort, that means each element will compare at the beginning of the list. And we compare with 0 and 1, we compare from the index 0 until the end of the list. So the comparison is still going on, and then it will become 2 plus 3 plus something until n, and then it will be n times n minus 1 divided by 2 n minus 1. This will be the formula to do the efficiency. And then the insertion sort will be applying big O notations. So the n squared, and remove the coefficient, and then it will become algorithm efficiency is 0 n squared. So similar with the bubble sort. Okay. Now the last one would be the quick sort. Somehow quick sort is difficult or hard to understand the concept. You may like to Google this all quick sort. We have a lot of example. Try to do that. I'm trying to focus on this quick sort lecture, and then try to make you all understand. Okay, it was introduced by CAR Hoa, and then the quick sort followed the concept of bubble sort. It has the exchange value between two elements. Right. The method is that we have an element that we can take it as a pivot. Somehow any person can call it as pivot or pivot. The pronunciation would be the pivot. Okay. So there are several exchange of elements happen until all data from the left pivot are smaller than the elements from the right pivot. Okay. So the exchange between data would be between smaller lists. Okay. So the same process is repeated for each of the sublists in the left and in the right of the pivot. So consider the list below: 8 to 11, 5, 15, 3 and 7. Okay. Now to identify the pivot, we can have any numbers here as a pivot. We can have pivot in the beginning, or pivot in the last of the list, or in the middle. It's up to you. First we need to identify the pivot. So let's say we have 8 as a pivot. That means we take the first element as a pivot, and then the rest of the element here we will process by having 2 pointers from left and right, and then make sure that all elements less than the pivot will be moved to the left, and all the elements that are larger than the pivot will be moved to the right. Okay. So let's say we have this array. Start with 8 pivot. Okay, and we have the left pointer and the right pointer. So first, actually the left pointer start with the second element, and the right pointer start at the end of the list. Okay, so the left pointer when point to the second element, it will compare with pivot. Is it 2 less than 8? Yes, that means it will not do anything if the pointer move to the third element and compare with the pivot. 11 is less than 8? No. That means we need to move to the right. So now check with the right pointer. 7 less than 8? Yes, that means we need to move 7 to the left. So we can swap this 7 and 11 together. It will become like this. So now 7 is in the left side of the list, and 11 is at the right side of the list. So it will become almost similar to this ascending order. Okay. Now we move on from the 7th, and then with the 3rd, the left pointer will be at the 4th element. After 7, we will move to the 4th element, and then it will compare. Is it 5 less than 8? Yes. So we move on. The second pointer move to the 15. So check 15 less than 8? No. So we have to check with the right pointer. So once it will be at 11, now we move the pointer to the second last element, and then we check. Is it 3 less than 8? Yes, that means 3 and 15 would be exchanged and swapped together and become like this, and 3 15. So 8 to 7 5, 3 15 and 11. So you can see that the first part or the beginning part of the list is smaller than the pivot, and the last one will be the larger or bigger value than the pivot. And then we move the pointer to forward, the left pointer forward, and then the right pointer also forward, pointer to the left. So if the condition is that if left pointer index bigger than the right pointer, that means you can stop the loop. Now once we know that the third element is at the end of the list that is smaller than the pivot, then we need to exchange the pivot with the last element of 3. So exchange with these two data, 8 and 3, become 3 and 8. So now we can see that 8 is at the right location, is at the middle. It means the left side of the 8 will be the smaller than 8, and the right side of the 8 will be the larger element, larger value of the 8. Okay, now we can continue and repeat until the sorted list is construct. Okay, so after this will be the first loop, the first process, and continue the process, but only for the left element and then the right element. We just take this 4, take out, and do the sorting. The same process as quick sort using pivot. Okay. Now we can draw like this a sequence diagram for quick sort. Let's say we have 8, 2, 11, 5, 15, 3, and 7, and then we take 8 as a pivot, and then whatever is less than 8, we just move or create a new list for a smaller than 8. Of course, it's the same with the right element that is larger than the pivot 8. And then apply the same concept that we need a pivot for this list. So 3, 2, 7, 5. So let's say 3 as a pivot, and then will become here, and then which one is the smallest? 2. 2 will become at the left side of the list. And then the 7, 5 will become the right side of the list. for the 3 value, 3 pivot. And then the left we have no longer need to do the comparison, then the 2 will remain in the sequence diagram. Same goes with 7 and 5. So we need to check 7 as a pivot, and then 7 as a pivot, and then 5 will become on the left side of the 7, and there's no more here unless we have a pivot 8. And then 5 we move to the left, it means we only have 5 value for the right side, the third level of the 8 pivot. Okay, so the elements that have a larger or bigger value than the pivot, so 15 and 11 will be at the right side. So apply the same concept. We have 11, let's say here 11 as a pivot, and then move 15 at the right side, and there's nothing in the left side, and then we check there's no more process need to be done, and then we can say that the list is being sorted in ascending order. So how we going to have the value is that we only tackle the concept here. So the answer will be 2, 3, 5, 7, 8, 11, and then 12, and then 15, sorry, and then 15. Right, so this will be the another example. Another example is that we take 70, the last element, as a pivot, and then taking all the other elements, if less than 70, will be moved to the left, and then whatever is more than 70 will be moved to the right. So in the left side, we apply the same concept. We need to identify the pivot, the last element, 5, that means 10, 30, 40 will be at the left side, and there's nothing at the right side. So when we have 1, 10, 30, 40 in the left side, then we need to identify which one is the pivot. So last element is the pivot, 40 will be the pivot, and then move to the the 10, 30 elements is less than 40, they move to the left, and then the right, there's nothing for the right. So apply the same sort, 10 and 30. 30 is the pivot. Okay, so last element will become a pivot. Then you just move 10 to the left, because 30 is larger than 10 or 10 less than 30. Okay, then the process here on the left will be completed. Okay, now we move to the right side, 80 and 90. So 80 we take it 80 as the pivot, and then we compare 80 and 90. 90 is bigger than the 80, then 90 will become the last element for the sorted list. And then what we're going to say is that from this 10, 80, 30 until 70, the sort process will become 10, 30, 40, 50, 70, 80, 90. And that will be the example for sort. Another example here, we have a list of 9. So array of 9. So we take pivot, the last element as pivot, 3, and then we compare each element here with 3, and we can move to the left, and also we move to the right. Okay, and then they continue the process until it will reach at the end of the tree. So the example will be -6, -3, 2, 3, 5, 6, 8, and 9 will be the sorted list for quick sort. You also can draw like this. similar to the previous, but the pivot we taking at the middle. So if you take 4 at the middle, and then whatever number will move to the left. Okay, so apply the same concept 3, and then only the same and the low, the smaller, 2 smaller than 3, then 3 will become at the right side, so there will be the 2 3 3. So this is the first 3, this will be the second 3. So sort stability. Okay, and then for we move down here, and the element that is larger than 4 will become at the right side, apply the same concept, will become 5 6 and 8. So we repeat, or we write the answer will become 2 3 3 4 5 6 and 8. Okay, so what will be the quick sort efficiency? So the worst case is that the algorithm is when the list is in the reverse order from desired order. So same goes with the insertion sort. Okay, but the time execution for this case will be O(n squared), but the processing time to accomplish for quick sort will be the n log n. Okay, and then of course the sublist that contains less than 20 elements will be beneficial, but in this case this quick sort is less efficient because it needs to apply the same quick sort on the left side and the right side of the tree, of the array. Okay, that's it. Thank you very much. Bye.